Alright guys, so I've got an NMR question here and I'm going to approach it slightly differently than normal, and I'm going to attempt it as if I'm in an exam. So I've not actually seen the mark scheme for this yet, so I'm just going to go through it exactly like I would in an exam, and then I will try and explain my thought process as I'm doing it, just so you can see exactly how I would think. So pause the video, have a go if you want, and then see if it kind of matches with my solution. Okay, so let's just read the question first quickly. So sodium ethanoate reacts with 2-methyl propanoyl chloride to form an organic compound Z and then NaCl as well. The molecular ion peak in the mass spectrum is 130. The IR spectrum shows 1820 and 1754. And then the carbon-13 NMR has 5 peaks, And then you have the proton NMR, which is shown. And then the question asks, deduce the structure of Z, showing how your answer is consistent with all the information provided. Okay, so I think what I'm going to do is I'm actually going to deduce the structure of Z right now without even analysing any of this information here. I'm only going to use the first line, which is this stuff. So we've got 2 reactants, and then we've also got a byproduct. And because we've got the structural formula of each of the reactants, and then we've also got the byproduct, we can quite easily work out the main product, which Z would be, just by using the structural formulae of the reactants. So let me just do that quickly, and we're going to write it down. We're going to kind of draw out each of these products and then kind of form them together. So let's start with the sodium ethanoate. So sodium ethanoate would just be, let's see, CH3, okay. So it'll be CH3 here, or actually I'll write it like this properly. So CH3, and then C, and then it'll be O double bond, and A like so. And then in terms of the other reactant, that is 2-methyl propanyl chloride. Now, if you notice, we have an NaCl as a byproduct, like I said. So that would mean that an Na from this reactant has to be discarded, and then the Cl from the acyl chloride also has to be discarded. So I'm going to draw those Na and the Cl groups near each other, right? So I'm not going to kind of draw it from left to right like it's shown here. I'm kind of going to go from right to left. So I'll start with the Cl here. Then I'll connect that to a carbon, which is connected to a double bond O. And then it is a carbon and hydrogen attached to 2 CH3 groups. Perfect. So these 2 react together, and because our byproduct is NaCl, these 2 just kind of cancel, right? And then we have to just combine the products together. Now, if we do that, we would get something that looks like this. So we have that, and so what I've done is I've just connected the O here to the carbon here, because this and this have cancelled out. And then I end up with this. So I'm going to move this down slightly, just because I don't want it to hit my other formula. But let me just move that down slightly. And remember, it doesn't have to be that neat. Like, you can do some rough workings as well, in order for it to help you. As long as the examiner can understand what you're doing and they can see your points clearly, it doesn't really matter, to be honest. Okay, so this is the final product that we end up with using the information from the question in terms of the first part. And that should be the right formula, because it's already given us the structural formulae of the reactants. So what you should notice about this is this functional group basically means that it's an ether. Now, if you've done some of your organic required practicals, you would know a bit about an ether. So all you need to know, to be honest, is that this is its functional group, okay? So we've got that now. Now we can just kind of use the information in the question. So let me just tick that off. So that's another thing I would recommend, kind of ticking all the information off as you go. So the molecular ion peak is 130. So that means, the MZ, or the molecular ion peak, means the molecular mass of the product. And usually in an MR spectrum, so say this was a mass spectrum, the peak would be at the very end, and this would show 130. So this would be 130, for example. So all we need to do is we just need to add each of the masses up and then see if we get 130. So I don't have my calculator on me, but I'll just try to do it in my head. So we've got 3 oxygens, so that would be 48. We've got 1, 2, 3, 4, 5, 6 carbons, so 6 times 12 would be 72. And then we've got 3, 6, 9, 10 hydrogens, and that does add up to 130. Perfect. So we know we're on the right lines. So we can take that off, and then our point would be the molecular mass of product Z is 130. Perfect. That's the first mark done already. So the second mark now, the infrared spectrum of Z has peaks at 1820 and 1754. Okay, so we need our data booklet here, which I've got opened up. So if I look, so I'm just going to do like a subtitle, IR, and then I'm going to do 1820 centimeters to the, what is it, to the -1. Perfect, centimeters to the -1. And then I'll show exactly what peak or what functional group that represents. So where is this here, right? So we're looking for, so we said that this was an anhydride. So we're looking for anhydrides. That should be here. Perfect. So we've got carboxylic acid anhydride, and then that correlates to 1850 to 1800, which is perfect. It's right in the middle. So we say this is an anhydride functional group, which is present in the product in Z. Perfect. So now we've got the 1820 done, so we can kind of tick that one. Then it's the 1754. So 1754 centimeters to the -1. So let's just look at our product that we've drawn, and let's see like what other functional groups there are. So we've done the ether. Now the only other thing I'm really noticing is the maybe the CO bond. Let's just see. So 1754 is what we're looking for. So let's just kind of scan the document, and it looks like, again, it's a C double bond O actually. So if it's a C double bond O and it's 1754, so that would mean it looks like it would be, again, a carboxylic acid anhydride. So as you can see, both of these peaks come up when there's an anhydride or carboxylic acid, and both of our kind of wavelengths from the peaks kind of match with these two. So that kind of reinforces the fact that it's an anhydride. So we can say again, this is an anhydride functional group, which is present in Z. And then I guess we could say the wavelength range for the anhydride is, what is it? It's 1850 to 1800. Is 1850 to 1800, and 1790 to 1740, and those kind of both match with the peaks that the question has said. So we can take that one off now as well. So now it gets slightly tricky where we get into the NMR stuff. So the carbon-13 NMR spectrum of Z has 5 peaks. Okay, so here we just have to use our product. So let me just do CNMR to kind of label it. And we need 5 kind of environments, 5 peaks. So we said we had 6 in total. So we can already tell that this carbon here and this carbon here, they'd be in the same environment. And the reason for that is because they're symmetrical. Because if we look at the carbon that's attached, we have a CH3 group here, same CH3 group, and then an H. This is directly symmetrical, like going across like that. We have a line of symmetry, which means that the carbons here, this one and this one, they're in the same environment. So we can count that as one environment. So I'll just change my color. Go one environment, so environment one, sorry. Then all of these carbons are in different environments because there's no more symmetry, right? You might think that this carbon and this carbon are in the same environment, but if you look, this carbon here is attached to just the CH3 group, whereas this one here is attached to this big group here. So it's not in the same environment, right? So let's say this is environment 2, this is environment 3, this is environment 4, and then this is environment 5. Yeah, so there's 5 carbon environments, and the fact that it has 5 peaks means that it has 5 environments. So that information also kind of lines up. So we can say 5 peaks equals 5 environments, and product Z has 5 carbon environments. And then I would also make sure that you do label the environments just so your examiner can see like exactly what you mean by environments, just so they know what you're talking about basically. So we can also mark that as complete. So a simplified high resolution proton NMR. So we've got the NMR. Now we've got to kind of analyze the NMR spectrum. So we have, what I like to do with NMR, whenever I get a spectrum like this, I like to label each peak. So I'm going to label this A, label this B, label this C. And whenever I get an NMR question and I'm kind of explaining the peaks in a written answer, I like to split it into 3 different things. So I like to split it into the splitting, the number of hydrogens, so the peak area thing, and then also the shift, the chemical shift. So we're going to start off with A. And the fact that we've already drawn out the molecule kind of really helps. So actually, before I do that, I'm just going to make another quick subheading with HNMR. Okay, so let's start off with A. So A, so in terms of our splitting, we've got a doublet. And it's a doublet because there's two like peaks, right? One here, one here. And if it's a doublet, that means that the adjacent carbon to this hydrogen environment has only one hydrogen attached to it. So you should know this from NMR using the n+1 rule. Okay? So if it's a doublet, the adjacent carbon has one hydrogen attached to it. So we can explain that. So we say, therefore, adjacent carbon has one hydrogen attached, right? Okay, so now we've done that, then we can go on to the peak area. So peak area, and that was, what was it? It was 6. 6, so there is 6 hydrogens in this environment. So if you have a peak area of 6, that's basically the amount of hydrogens you have in the environment. In this environment. Perfect. Okay, so that should instantly scream to you that it has something to do with these, because these carbons and these hydrogens are both in the same environment, similar to this. So these carbons here were in the same environment. The same thing goes for these hydrogens as well, because there is symmetry, right? So those two are also in the same environment. So we can directly say that peak A corresponds to these 2 environments here. So I'm going to label it in another color. I'll just say this is A, right? Just to make sure the examiner knows what I'm talking about. And then we can follow that up and we can say that the adjacent carbons, so bear in mind the environment that we're talking about is on this, and the carbon that the hydrogen is attached to is these ones here. So we look at the adjacent carbon, which is this one, and then we can see that this carbon here is only attached to this one hydrogen, which is exactly what we said, hence why it's a doublet, right? So that also kind of lines up with that information. So we can kind of affirm that. Now what we need to do is we need to do the shift, right? So the chemical shift, and we can see that this carbon is purely just attached to, obviously, methyl groups, a hydrogen, and then another carbon with the double bond O. And we can see that that shift is at around, what's that, like 1.2 kind of. So let's just go to our NMR thing here. And if we see 1.2, the only thing that we can really spot is this one, so the HCC bond, so it's the alkane. So we can say that the group is the HCC. So write the group directly from the data book. And the shift is approximately 1.2. You can just say that. And then that's it. That's all you need to write. So that's peak A done. So we can take peak A off. So now we just do the same thing with peak B. So B splitting. So we can write the equals. And then we've got for peak B, we've just got a singlet. Okay. So if we have a singlet, that means that the carbon adjacent to whatever environment this is representing has no hydrogens attached to it, okay? So we can say, therefore, the adjacent carbon, you can write to this environment as well. I don't think you have to, but we'll write it anyway. Environment has, how many, it was a singlet, so it has no hydrogens attached to it. Again, using the n+1 rule. If you don't know that, just watch some of my previous videos and you can find out about it. But I'm not going to explain it here, otherwise the video is just going to be way too long, okay? So, we've done the splitting now. Now we just need to do the peak area. So, peak area here. And then we can say that the peak area is 3. So that means, therefore, so if it's 3, that means there's 3 hydrogens in this environment. Okay. So now we can just kind of look at our product again, and we can kind of gauge what peak this represents. So we said that the adjacent carbon to this hydrogen, the adjacent carbon to this environment has no hydrogens attached to it, and this environment has 3 hydrogens. Well, it's quite obvious, but it's clearly going to be this one, and I'll explain it, because this environment here, there's 3 hydrogens, so that ticks off one thing. And then the carbon adjacent to it, so remember, this isn't the carbon adjacent to it because these carbons are directly attached to the hydrogens. We're looking at the carbon adjacent to it. So the adjacent carbon, which is this, clearly is not attached to any hydrogens. So that would mean that it would be this environment for peak B. So we can label this as B. Now all we need to do is a shift. So the shift is around like, what, 2.1 again? 2.1, yeah, 2.1 to 2.2, something like that. It doesn't have to be exact, to be honest, but shift, and then because it's 2.1, let's see. So we can clearly see that it's attached to a C double bond O. So this is attached to a C double bond O, and then also the 3 hydrogens. So if it was 2.1 to 2.2, that would mean that it has to be this group here, this H-C double bond O. And we can directly see that because it will be the hydrogens here attached to the carbon, attached to the carbon here, attached to the double bond O here. So it kind of mirrors exactly. So we can do HCC double bond O, and then we can say the shift is 2.1 to 2.2. Now, one thing I did forget to do actually in this part was mention the functional group itself. So the functional group is the alkane functional group. So I'm going to write that here. And then this functional group here, where is it? Here. So this is a C double bond O. So this would be a ester, right? Because this group here is an ester. Obviously, the whole thing is an anhydride, but it's kind of like two ester groups just joined together. So we're going to say it's an ester. So we can write functional group is an ester. Okay, so we're nearly done now. So we've done peak B. Now we just got peak C, and this one looks a bit peak. So let's just do it in this part, yeah? And by the way, you can write in this page here, because I did that in my exams. So I was very worried that this wouldn't get marked, but I found out that it did get marked, so it was fine. So if you need to, and you're at EDEXCEL, you can write on these blank pages. It's not an issue. So with this one, so again, splitting. So the splitting here is, oh my god, okay, what is this? So these tiny peaks here, I know it's really badly drawn, but they count as peaks, I think. So we have 1, 2, 3, 4, 5, 6, 7. So we've got a septet here. And again, using the n+1 rule, that means that we have 6 hydrogens bonded to the adjacent carbon, okay? And that doesn't really make sense, right? Because you can't have 6 hydrogens bonded to one carbon. But then, using your common sense, you would figure that it's to do with the hydrogens being in the same environment, okay? So I'll get onto that. So septet, meaning there are 6 hydrogens attached in total, say. So don't say 6 hydrogens attached to a carbon, because that doesn't make sense. So we can say 6 hydrogens attached in total, meaning 3 from one group, 3 from the other group, to the adjacent carbon. And if you want to be really specific, you can say 3 hydrogens from each environment. Okay? So that's the first thing. That's the first kind of thing that we do. Next thing is the peak area. So peak area, I'm pretty sure it was 1, right? Yeah, so it's 1. So it's 1, therefore 1 hydrogen in this environment. And then finally, we have, where is it? So yeah, sorry, we got one hydrogen there. Okay, so now if we look at our product, we can already really tell what this would be. And this would be this hydrogen here. And the reason for that is one hydrogen, it's a single hydrogen in one environment, which means it kind of matches up with our peak area of 1. And then we have the carbon, which it's attached to, which is this. And then we're looking at the adjacent carbons. But notice that because these two groups are in the same environment, we can count them as 1, okay? So we can say that this carbon here is attached to 2 of the same CH3 groups in the same environment, and the total number of hydrogens is 6 for both of them, right? Because we have 3 here and 3 here, which would lead to 6. And then obviously using the n+1 rule, that would mean that it presents a septet in the NMR spec. So again, that kind of aligns with our data. So we can say that this is C here, right? And let me just get rid of that. And bear in mind, these carbons, obviously, they don't have a label because there's no hydrogens attached, which means there is obviously no peaks here. So we said that there was 5 carbons, but we've only got 3 peaks because these carbons don't contain any hydrogens. So actually, to add on to the HNMR, we can just say there is 3 hydrogen environments. Sorry for my horrible handwriting, by the way. So there's 3 hydrogen environments, which means 3 peaks on the spectrum perfect. And that, I believe, is everything, okay? And I think, yeah, so I've used all the information, and I'm very confident that I've got it right. So I'm not actually checked the mark scheme, but after I film this and stop recording, I'll quickly check it, and I'll make sure to let you guys know if I've made a mistake or if I'm missing a point or anything, okay? But I think that is everything. So I hope you found it useful, kind of a different style of video today, just going through the question. I know it's long, but I wanted to show you exactly how I would approach a question like this, and there's a lot of writing as well. But yeah, so make sure you guys obviously like, follow, comment, share, and if you're interested in getting tutored by me, I offer services in biology, chemistry, and maths at GCSE and A level. So be sure to get in touch through DM if you're interested in that. Alright, guys. So I've just checked the mark scheme, and everything went well. It was just one tiny silly mistake that I made in my workings out, and I simply just forgot to mention the shift. And obviously, this was the end of the question. So I kind of just completely forgot about it, to be honest. So yeah, make sure you don't do that. But other than that, I think everything else was perfect. The only other thing I can kind of think of is the fact that with the bonds, when kind of drawing out the group to represent each peak in my explanation, I just wrote what was shown on the NMR data booklet. But I think it should have been fine because I labeled each of my environments in my molecule. So I'm not too sure if that's an issue or not. I don't believe it is. But yeah, other than that, everything was perfect. So kind of take that as a guide as to how to approach these types of questions.